I wanted to do a quick tutorial on doing parametric solutions or general solutions because it seems to be one of the things that's tripping up a lot of people, and I'm hoping to answer just a whole bunch of questions in one shot here with this quick tutorial. Okay, so first off, I want you to go all the way back to Module 1, and remember, we're talking about ax equals b, but that's really representing a set of equations. So we have a11 x1 plus a12 x2 equals b1, and a21 x1 plus a22 x2 equals b2. Okay, and that was our standard format. We put all of our equations into this format, and then that allows us to move them into ax equals b, okay, which was a11, a12, a21, a22, multiplied by x1 and x2 is equal to b1, b2. Okay, so we had that set of equations. We can move them into a matrix format, which allows us to just write it as ax equals b. Okay, but you have to remember that those equations are sitting in the background for a lot of this, and you need to be able to remember how to go back up to here. Okay, that's quite important in being able to solve these. Okay, so for general solutions, we have been augmenting things. So we have augmented a matrix A with B. We do some Gauss-Jordan, and we ended up with a reduced row echelon and some vector C. Now, if there was a single answer, then R would turn out to be an identity, and it would be augmented with X. Okay, so this would be when you had an invertible matrix A. So if A was invertible, you would get that I and X. If it's not invertible, you get the R and C. Okay, so I and X is what we would love to get. Same number of equations as unknowns, and we would be able to find a single answer. In the case of parametric solutions, we end up with this R and C type thing. Okay, so we don't have enough equations to fully constrain our variables. Okay, so let's take one quick example here. So we could take a matrix here, -2, 0, augment that with 1, 0, 0, 1, 3. Okay, so here is R, here is C. Okay, so we started with some ax equals b. Turned out one of the equations that we had was actually dependent on the other one, so that when we did Gauss-Jordan, it disappeared, and we were left with only 2 equations, 3 unknowns. Okay, so our unknowns, you'll remember our x, well, we'll have x, it has 3 components, x1, x2, and x3. Those are our 3 variables. Now, again, x1, x2, x3, we're just using an arbitrary variable for that, or an arbitrary demarcation for that. It could have been currents and voltages, it could be colors, it could be temperatures, it could be, you name it, it can be it, okay? But we're just using x1, x2, x3 just because we're being general at the moment. Okay, so if we want to take this R and C, this augmented matrix, and put it back into the equation form, okay, we can remember that what we have here is R times X equals C currently, okay? And if we did that, what would we get? We would get x1 minus 2x2, 0x3, and 1. And our second, so that was our first row, it became that. Our second row here would tell us what? It would tell us x3 is equal to 3, right? Because we're multiplying this out, and so this column would get multiplied by x1, this column will get multiplied by x2, this column will get multiplied by x3. Okay, so we've got our 2 equations here, or the 2 equations that we have, we've moved back into the equations just so you can take a look at them. Now, we don't have as many equations as we have unknowns, And so we won't be able to find a single answer. We're going to end up with a general solution. So the best thing to do is circle your pivots. Okay, so there's my pivots circled in blue. Okay, now a bunch of you guys have been looking at this and saying, okay, my third row has zeros, therefore my third variable is my arbitrary one. Not the way to think about it. You're looking for which columns have pivots in them, because those are sort of the equations that are dedicated to those variables. So we have this one here, only x3 appears in it. And in this one here, we have both x1 and x2, but generally we would pick the leading variable as the pivot variable and call the other, or whatever's remaining, our free variable. Okay, so what does that mean? That means x2 here does not have a pivot in its column. Therefore, there's no equation that's sort of dedicated to telling us about x2. x2 is our free variable. Okay, so x2 will be equal to t. We'll call it t. And so we can also write x3 down here. So x3 is equal to 3 in this case. Okay, and x1 will be equal to, swapping t into there, we have 1 plus 2t. So x in this case equals 1 plus 2t, t, and 3. Okay, so you'll notice that t doesn't appear in all of those terms, so we can't pull it out. That would be the general solution to that set of equations. If we pick some value for t, okay, it sets the value for x2, which in turn sets the value for x1. And then we'd be able to find a solution. Again, the equations that we were given originally did not give us enough information. There was one of them that was not independent. Okay, so, just to make things clear, this was a 2x2 that I showed here. This is a 3x3. Okay, just in case you thought those two were perfectly related, they're not. Okay, so that would be a general solution, okay, or a parametric solution to just a set of equations. Now we'll go on and look at the homogeneous case. Okay, homogeneous equations. Okay, so homogeneous equations are ones of the form ax equals 0. Okay, so it's equations where our constants column is all zeros. Okay, so what would we do? We have a augmented with 0. We do a little Gauss-Jordan, and we would end up with our reduced row echelon augmented with a column of zeros. Now, because it's equal to a constant column of zeros, and that's not going to change, we tend not to do that, and all you do is have a, do Gauss-Jordan, and get r. Why? Because we don't need to keep that column of zeros around. We know it's still there. Okay, so we know that ax equals 0, and also rx will be equal to 0. Okay, so it's going to be the same solution for both ax and rx, because in doing Gauss-Jordan we were solving ax equals rx, and ax equals 0, and we got rx equals 0. It's the same thing. Okay, so that was our reduced row echelon. So let's do the reduced row echelon for that last, the same example that we just did, only this time we have a 0 constant column. So minus 2, 0, 0, 0, 1, and 0, 0, 0. Okay, so that's our r times x is equal to 0. Sorry, those are zeros. Okay, r times x equals 0. Okay, it's not the constants column that we had before this. We're looking for the homogeneous solution, so ax equals 0. Okay, so we could write out those equations. What would we get? x1 minus 2x2 equals 0, and x3 equals 0. Because again, remember, when we do this multiplication here, do this multiplication here. It's multiplying our first column by x1, second column by x2, third column by x3. So where are our pivots? We have a pivot in that column, pivot in that column. x3 is the only one that doesn't have one, and so that's our free variable. Or sorry, x2 doesn't have a pivot in its column, and so it's our free variable. So x2 will make it equal to t. Okay, and so what does that get us? That gets us x3 is equal to 0. Okay, so that was just right here. x3 is equal to 0. And we have x1. If we were to add 2x2 to both sides, that would put the equal sign there. And so we have that equal to 2x2. x2 is t, and so we have 2t. Okay, and we could just put that into a matrix. So we would have 2t, t, and 0 is equal to x. Okay, and we could pull the t out so that we would have t times 2, 1, 0. Okay, so that would be our general solution to ax equals 0. Okay, and so that's all possible answers for ax equals 0. This doesn't have a trivial solution. It's not just the 0 vector. Okay, and so that is the parametric solution or general solution to ax equals 0. Now, the general solution to ax equals 0 is your null space. Okay, so it's your null space for A. Okay, because your null space is all possible solutions to ax equals 0. Okay, that is all possible solutions to ax equals 0. Any value of t will give you a vector that if you multiply that by a will give you 0. Okay, so, well, let's do something here. So let's set t equal to 3. Okay, so what would we get? We would get 1 minus 2, 0, 0, 1. Multiply that by 6, 3, 0. And that would give us, that would be 6 minus 6 equals 0. And 0 times 1 is 0, and 0, all that stuff times 0 is going to be 0. Okay, so it's just 0, 0, 0. Okay, so again, t minus infinity is less than or equal to t, which is less than or equal to infinity. Okay, t can be anywhere in there, and we get a null vector, or a vector that when we multiply it by our matrix A will give us a null, a 0. Okay, so that's why it's called a null space, because any vector in that set, okay, is going to give you a null answer. It is the solution to the homogeneous equation. Now, eigenvectors are just eigenvectors okay, they are just the null space of A minus lambda I. Okay, we call this thing B. Okay, so eigenvectors are just the null space of B. And the way we derived the eigenvalues, we used determinant equal to 0. We went from the equation determinant of A minus lambda I equals 0. If the determinant of that, okay, so that's basically just the determinant of what we're calling B here. Okay, the determinant of B is equal to 0 means that it's not invertible. If it's not invertible, that means it has a rank less than, or non-full rank, does not have full rank. Okay, it means that there's something sitting in the null space, and it means it's not invertible. Okay, so not all of those rows are going to be independent because we have a determinant of 0. Okay, so we use that to find the eigenvalues in the first place, which means that when we do A minus lambda I, we are definitely going to find something in the null space. Okay, so it's not going to be just the trivial solution. So you'll go through, you'll do A minus lambda I, and it is going to give you some kind of matrix. Okay, so well, we could do something, I don't know, 1, 0, minus 2, 3. Okay, and another one here, 0, 1, 1, 1. Okay, so say we did it all and we got this matrix. It's a 3 by 4. If we had run that, this would be, say that was B. Okay, and we'd already taken it to some reduced row echelon form of B. Okay, so we're trying to figure out what Bx equals 0. We're trying to find all solutions to Bx equals 0. So we took B, we took it to reduced row echelon, just as we did in the top half of this slide. Okay, and we found our R, and here's our R. Okay, so we're just doing Rx equals 0 and finding the general solution. The general solution to that will be the null space of B here, which is the null space of this A minus lambda I. Okay, so the null space of that is your eigenspace. It's the space that contains all of your eigenvectors. Okay, so what would we get here? We have x1, x2, x3, and x4. Okay, we have a couple of equations. We have x1 minus 2 x3 plus 3 x4 equals 0. And we have x2 plus x3 plus x4 equals 0. Okay, so we only have those two equations. Okay, our leading ones are there, so there's our pivot. Okay, which means x1 and x2 are our leading variables, which in this case, we still have two columns here. So we have x1, x2, x3, and x4. Okay, these two do not have a leading 1 in their column. Okay, no pivots in those columns, and therefore those are two free variables. I, of course, have run out of space, but we'll make this work. Okay, so we'll go from there. Okay, so what do we have here? We had our two pivot variables, so we've discovered there are two free variables, should be x3 and x4. And so what does that tell us? That tells us that x3 is equal to r and x4 is equal to s. Why r and s? We just picked them because we needed two arbitrary variable names. Okay, so we can then write in x1 and x2. x1, get our equal sign over there, which gives us a plus and a minus. So that would be x1 is equal to 2r minus 3s, because x4 is s, x3 is r, so r and s. Okay, and so for x2, again, move the equal sign to over there, which gives us a minus and a minus. And that one is r, and that one is s. Okay, so x2 is equal to minus r minus s. Okay, now the other thing I'm going to do is just delete s there for a second. It's actually easier if I write s over here, because x4 is actually 0 times r plus s, and x3 is r plus 0s. Okay, so I can throw both arbitrary variables into each of them. It's just that it's 0 times the one and 0 times the other. And what that does is it makes it slightly easier, hopefully, to see that we can write this as 2r, scratch that, I don't want the r, 2 minus 3, and we're going to multiply this by r and s. Okay, so remember your matrix multiplication, that means this column's being multiplied by r, that one's being multiplied by s, and so we have 2 minus 3 minus 1 minus 1, 1, 0, 0, 1. Okay, and so that then is our general solution to Bx equals 0, which we reduce to Rx equals 0 with some Gauss-Jordan. Okay, we did some Gauss-Jordan, got that to a reduced row echelon, which is what we had here. Okay, there's our R. We're trying to solve Rx equals 0 because that's going to give us the null space of B. Okay, we did that. It gave us a general solution. In this case, we had 2 free variables. We had 3 equations, 4 unknowns. Okay, only 2 of those equations in the end ended up being independent, so we only have 2 leading variables, in this case x1 and x2, indicated by the columns where they have a leading 1. X3 and x4 were then our free variables. We assigned them arbitrarily R and S. We then found each one of the variables in terms of R and S, and our equations that were represented in R. Oh, sorry, big R. Now I got big R and big little r. That should be little r. Okay, and that allowed us to create a 2-dimensional null space, or find the 2-dimensional null space. Why is it 2-dimensional? Because this matrix R, or the original matrix A, or I guess B, the original matrix B, the rank of B was 2. Why was it 2? Because we only had 2 independent equations. We ended up with 2 pivots. So the rank of it was 2. Okay, and our row space is in R to the 4. Okay, so we're sitting in R to the 4. Why? Because our rows are 4 long. And so our null space, which is sitting in there with our row space, is all solutions to AX equals 0. X is 4 long. Okay, and so if our rank is there and the other is 4, that means the dimensions, okay, of the null space, or the nullity, must be 2. Right? It's going to be 4 minus 2 is 2. So we were expecting something 2-dimensional. We got something 2-dimensional, so that seems pretty good. And so this would be, or these vectors here, are giving us the basis for the eigenspace. So again, we could pick any value of R and S, and it would give us a vector that when we multiplied it by B would give us 0, or in the case of an eigenvector, AX, so if we multiplied it by the original X, A, so remember B was equal to A minus lambda I. Okay, so if we went back to the original matrix A times X, okay, would give us lambda times X. Okay, so the null space of B is going to be the eigenspace of A. Okay, and you find your general solutions as shown there. Hopefully that will help to clarify. I sure hope so. Good luck on your final exam tomorrow.